Welcome everyone. My name is Raffaella and I am a fifth-year medical student at the University of Exeter. Today I will deliver a webinar series on the health effects of climate change, and this is part 2 of the webinar series. And this was developed as part of the Medics.Academy virtual elective. So in part 2, we will cover the health consequences of air pollution and infectious diseases. So let's start with air pollution. It is estimated that 91% of global population is exposed to air quality levels that exceed the WHO guideline limits. So this is about 9 in 10 people globally. And approximately 4.2 million people die from outdoor air pollution each year. Meanwhile, 3.8 million people die from indoor air pollution each year. And mortality largely results from stroke, heart disease, COPD, asthma, lung cancer, and acute respiratory infections. So one of the major contributors to outdoor air pollution is ground level ozone. And this is formed from the reaction with sunlight of pollutants such as nitrogen oxides from vehicles and industry emissions, and volatile organic compounds which are emitted by vehicles, solvents, and industry. Excessive ozone at the ground level can cause a variety of health problems, mostly due to inflammation. So for example, inhalation of ozone can cause inflammation in the lungs, and this can cause breathing problems, trigger asthma, exacerbate lung disease. And the most vulnerable individuals are people with chronic lung and heart disease. Ozone can also cause burning of eyes, nose, and throat, and headaches. Particulate matter is another important air pollutant. And this is a complex mixture of small solid and liquid particles suspended in the air. There are different types classified according to diameter of the particles. And one of the most dangerous ones is PM 2.5, which means it is 2.5 microns in diameter. And this can, because it's so small, it can penetrate and lodge deep inside the lungs, entering the bloodstream. So research has shown that inhalation of particulate matter can be deadly by causing heart attacks and strokes. Also, chronic exposure can cause cardiovascular and respiratory disease and lung cancer. Particulate matter can be produced by combustion of fossil fuels, wildfires, burning domestic fuel for cooking and heating, and industrial emissions as well. So now let's move on to discuss infectious diseases. There are many infectious diseases, but we will look at malaria specifically and use it as an example to explain some of the changes that may be seen in the spread of vector-borne disease in the context of climate change. So malaria is a parasitic disease transmitted through mosquito bite. And although malaria is fatal in about 0.3% of cases, it represents a major global challenge. In fact, more than 200 million people each year contract malaria, and this is mostly in lowland tropical areas. And more than 400,000 people die, and this is mostly young children. And climate change matters to vector-borne diseases such as malaria for many reasons. First of all, insects are ectotherms, which means they're cold-blooded. So this means they're sensitive to the temperatures of their surrounding environment. So their biological processes such as metabolic rates, development rates, reproductive rates are all dependent on temperature. At the same time, the parasites carried by the insect vectors are also temperature sensitive, especially in the time the parasite spends developing in the mosquito. However, the relationship between temperature and malaria transmission is complex and shows many nonlinear aspects. So some of these nonlinear aspects are summarized here. Higher temperatures promote both higher mosquito biting rates and faster parasite development. However, at high temperatures, the predicted vectorial capacity, which is the rate at which mosquito bites can transmit infection, is reduced. So this means that at high temperatures, mosquitoes are less likely to transmit disease. Also, at high temperatures, there is an increase in mosquito mortality rate. So what does it all mean? Because mosquito and parasite metabolic processes are temperature dependent, warmer temperatures accelerate mosquito and parasite development, and they also accelerate malaria transmission. But then there is a point where temperature increases and becomes high enough to be lethal. So there is a sweet spot, which is the ideal temperature of malaria transmission, and it is about 25 degrees Celsius. in the future, there may be a shifting suitability for malaria. So some places such as East Africa that are now a little below the optimum temperature will reach optimum temperatures for malaria transmission with global warming. Other places such as West Africa, which are already at the optimum temperature, may become too warm, leading to a decline in malaria transmission potential. And the problem with this is that there is a big risk of large populations coming into higher risk of malaria transmission, depending on the local temperatures. And also the risk that potentially millions of people that haven't been exposed to consistent malaria risk before, or at least not at an endemic level, they are suddenly becoming exposed more and more often. So finally, keep in mind that the picture is much more complex. So other factors such as altitude, precipitation, urbanization all influence mosquito prevalence and disease transmission. And also, besides climatic factors influencing vector and parasite characteristics, there are also human factors. For example, human interventions that can be implemented to reduce vulnerability to infection. So this suggests that predicting future malaria incidents based upon effects of climate change alone may be difficult. And while climate change can create conditions that are either permissible or not permissible for disease transmission, just because you have suitable conditions, it doesn't mean you will have big outbreaks. And that is because of the economic development and vector control activities. So it is worth mentioning as well the biodiversity in the context of health and climate change, because one of the main questions at the moment is whether we should expect more pandemics in the future. Biodiversity refers to the biological variety of life on the planet in all of its forms. And biodiversity is essential for life in ways that may not be always apparent or appreciated. For example, it supports many human needs, including availability of nutrition, energy, fresh water, development of medicines, and all of these underpin good health. Climate change is contributing to biodiversity loss through things like land use change, pollution, ocean acidification, chemical and waste contamination, and long-term changes can cause shifts in the distribution of plants, pathogens, animals, and even human settlements. So biodiversity loss can have significant negative effects on human health due to the disruptions of the ecosystems that support our human needs. For instance, biodiversity loss may mean reduction in the productivity of soil or in the nutritional variety of food that is fundamental for health. Major processes such as deforestation, land use change, water management, urbanization, migration, all of these contribute to shifting in patterns of infectious diseases. Climate change may also lead to a biogeographical redistribution of species towards cooler temperatures. So as a result, we may see animal species moving into areas where humans are prevalent, and this will create a new human-animal interaction and potential opportunities for pandemics to evolve, particularly from zoonotic diseases, although these are still early days for research and predictions are difficult. And then there are also indirect effects, because indirectly changes in the ecosystem service affect livelihood, income, local migration, and of course, in some occasion, it may even cause or exacerbate political conflict. So the main take-home messages that we have covered in part 2 are that there are many air pollutants, including ground-level ozone and particulate matter. The groups most vulnerable to air pollution include the elderly and people with chronic disease. Relationship between climate change and infectious disease is complex, but a redistribution of vector-borne disease is likely based on the local temperatures. And also incidence of new diseases may be possible as a result of biodiversity loss. So this is the end of part 2. Thank you for listening, and make sure you check out part 3 of this webinar series, which you can find below in the description of this video.